Okay, hi guys. So we are from Group 1 for the subject Power System Analysis EEE3324. And today we are going to be presenting about our case study, which is Power Flow and Stability Analysis for Multiple Bus System.
So my name is Kian PE and my matrix number is 201025.
My name is Muhammad Hazib bin Raja, and my matrix number is 200812.
Sorry, my name is Muhammad Noaz Iman. My matrix number is 202781.
My name is Hazirul Mustaqim. My matrix number is 203236.
And my name is Kishan Kumar and my matrix number is 202744. Okay, so for the list of content, today our case study discussion will be talking about first the introduction, and then we'll move on to the journal that we have chosen. Then the question that we have approached using the bus network that we have got from the journal, and then the simulation results, the discussion, and the conclusion. So we'll go on to the introduction first. So for the introduction, so power system stability involves examining the behavior of a power system during disturbance. So it refers to the system's ability to recover and return to a stable state after being subjected to disruptions. And basically, power system instability occurs when the system experiences a loss of synchronism, where systems machine, whereby the synchronous machine deviate from the intended synchronization. And then here we can understand that there are three main types of stability which are important to be noticed and to be maintained. So the main three stabilities are steady state stability, dynamic stability, and transient stability. So steady state stability pertains to how synchronous machine responds when the load gradually increases, whereby dynamic stability is about it encompasses the reaction to minor disturbances within a system, leading to oscillations. The system is considered dynamically stable if the oscillation remain within a certain amplitude and dissipate rapidly. And for the transient stability basically deals with the response to significant disturbance, which can result in notable changes in the rotor speed, power angles, and power transfer. So it is a rapid phenomenon that typically manifests within a few seconds. So when these three stabilities are disrupted or if there's a problem in the network, these three stabilities are to be encountered first to solve the issue. And yeah, we'll move on to our next part, which is the journal. So this is the journal that we have taken for this case study, whereby we have obtained our 11 bus system from this journal, and using that we have conducted our fault studies and the stability studies.
Okay, so for the questions, this is the 11 bus system, the diagram for the 11 bus system. And next. Okay, so this is the table for the load data, which have the number of bus from 1 to 6, and then the load, the bus, and also the load. And then for the generation schedule, which included the bus number 1, 10, and 11, the voltage generation, MVR, and also the limits. And then next is the line and transformer data for the system. And next for the last table included the machine data. So the first question is determine the stability when A, the fault is cleared in 0.4 second, B, the fault is cleared in 0.8 second. The second question, repeat the simulation to determine the critical clearing time.
So now I will be proceed to the simulation result. So please allow me to share my screen. Okay, so this is the MATLAB file I have constructed, and this is the main file which consisting the programming to obtain the to analyze the stability and also evaluate the power flow solution. So to get the power flow solution, I choose a Newton-Raphson method, and this programming code shows is to calculate the power flow solution using that method. So in the main file, it also includes a LFY bus function, and this I use this file to run the function which to obtain the admittance matrix. Next, for TRS step function, it is to obtain the pre-fault bus admittance matrix, including the load admittance. Next, for bus out, it is actually a program to print the bus flow solution in a tabulated form, which is in the matrix form. And then for Y bus BF, the BF is stands for before fault. So it is to form bus admittance matrix before fault. And then for DF is during fault. So this program is to form the bus admittance matrix during fault. And this is the code to form the bus admittance after fault. Next, for this programming code is to analyze the state space variable representation during fault. And the last one, FPEK, is to analyze the state variable representation of the multi-system after fault. So this is the main file with the load data that mentioned just now. And I have in all the data available, and I'm going to run the program. So this is the power flow solution using Newton-Raphson method, and the number of iteration is 4 iteration. So now we are going to apply the fault at bus number 4. And then, yeah, this is the admittance matrix that formed by the program. So just now we have mentioned that we are going to determine the stability when the fault is clear in 0.4 seconds. First, we have to remove the number of lines which mentioned in the journal, which is 4, 9, and then we want to determine the fault clear in 0.4 seconds. So this is the result printed out in the MATLAB, and we have included this in our report. And this is the graph we obtained. So the second question is to determine the stability when the fault is clear in 0.8 seconds. So for 0.8 seconds, the graph will be like this. This is the phase angle difference diagram. Then the third question is to repeat the simulation to determine the critical clearing time. So the critical clearing time is actually the maximum time during which a disturbance can be applied without losing the bus stability. So it can be calculated with this formula. And the value obtained in the journal is 0.72. So the TC now is 0.72. And the final answer for this question will be like this. This is the phase angle difference that we obtained lastly.
Okay, so moving on to the discussion part. So for this particular study case, transient stability analysis is required for this case study. The case study involves a 3-phase line defect and examines the system stability under varying fault clearance time. Second, the both flow solution and reduced admittance metrics are obtained using MATLAB programs. This is the Newton-Raphson technique is used for power flow analysis, and the reduced admittance metric represents the circuit state before, during, and after the fault. So the power angle diagram provides insight into system behavior, just like Kim-Fei have shown before. The phase angle difference represent the system response to the fault clearance and its impact on machine behavior. So the first one, before fault, mechanical power equals electrical power, indicating a stable system. The system operates in equilibrium with equal mechanical and electrical power. Next, during fault, accumulation of unused power and system instability. This electrical power decreases significantly while mechanical power remains constant, leading to unstable conditions. The third one, after fault clearance. So in this phase, energy transfer and restoration of stability. The system returns to stability as the accumulated mechanical energy is converted into electrical energy. And last one, critical clearing time, which is the maximum time for fault clearance to maintain stability. These faults must be cleared before the critical clearing time to avoid system instability.
All right, so the results indicate a critical clearing time of the 0.72 second for the given case study. At 0.72 second fault clearing time, the system shows oscillatory behavior with a peak-to-peak gap larger than at 0.4 second, indicating its critical stability. So the system stability at 0.4 second fault clearing time and instability at 0.8 second fault clearing time. At 0.4 second, the system is stable as the electrical energy oscillates properly. At 0.8 second, the system becomes unstable due to the accumulation of excess mechanical energy.
Okay, so for the conclusion part, so from the experiment, we were able to understand that the experiment highlighted the criticality of the precise fault clearing, as any delay can lead to the system instability. So the timing of the fault clearing, which is specifically when T1 is less than TC, which is the critical time, it ensures system stability. And when T1 is equal to TC, the system reaches a critical stability point. And when T1 increases above TC, the system becomes unstable. So the key takeaway from this whole case study is we were able to understand that the problem of multiple fault detection and classification in power system has a great importance for the economic operation of the power systems in nowadays competitive electricity markets. So it provides a quicker repair of a system, which improves the system availability, performance, and restoration time reduction and effort of maintenance. Hence, it will increase the system reliability. So by fixing all of this fault and by overcoming this fault as soon as possible, it helps to provide a better transmission of power with undisrupted and uninterrupted transmission. So thanks for watching our presentation, and this is our case study, and thank you everyone.
Right, thank you.